Yes, ma'am.
Okay. So let's start with a little bit of a recap. We looked at this problem in the last class of trying to motivate a probability distribution. So we saw that there were various kinds of probability distribution, and the one we started with was the binomial distribution. The binomial distribution comes when we think of an event which can result in one or more, which can result in one of any two outcomes. So you can think that the event is that you are trying to look at smoking status. In that case, each of your interviews is the event, and the two outcomes are that the person might be a smoker or might be a non smoker. We think of n independent trials. By trial, we just mean repetition of the experiment. We assume that the probability of success. Now, we have two events. It doesn't really mean that one is a success and one is a failure. We just label the events as success and failure. You can choose to call a smoker a success, or you can choose to call a non smoker a success. It's up to you. So, we assume that we have these two events which are arbitrarily labeled as success and failure. Pi is the constant probability of success over all of the repetitions of the experiment, that is, all of the trials. In that case, if the variable we are interested in is the total number of successes, so for the smoking experiment, it would be the total number of smokers in the study, we say that x follows a binomial distribution with parameters n and pi. In this case, x has the probability mass function as given here. So the probability of capital X equal to small x is given by n choose x times pi to the power x times 1 minus pi to the power n minus x, and this holds for x equal to 0, 1 up to n. So for example, if n is 10, which means that you repeated this experiment 10 times, you interviewed 10 people in trying to find the proportion of smokers, and you wanted to know what was the probability that you observed 5 smokers, then you would put in small 5 in place of small x in this expression, and f of 5 would be 10 choose 5 pi to the power 5 into 1 minus pi to the power 10 minus 5, which is also 5. This distribution we saw has the probability that its mean is n pi and its variance is n pi into 1 minus pi. It's possible to show that the variance n pi into 1 minus pi is always less than n pi. So the binomial distribution has the property that the variance is smaller than the mean. For the case when n is equal to 1, which means that we only perform the experiment once, we have the similar distribution, and this distribution is a special case of the binomial distribution called the Bernoulli distribution. You can check that in this case, the PMF will become f of 0 equal to 1 minus pi and f of pi equal to f of 1 equal to pi. We also introduce the negative binomial distribution where the basic setup is the same, which is that we are repeating some trial which can result in one of two outcomes. The probability of a success is constant from trial to trial. However, my random variable is slightly different. So I don't, in this case, decide that I'm going to stop at n trials and observe the number of successes. Instead, I decide that I'm going to keep repeating the experiment until I get some specified small r successes. So if r, for example, is 6, I'm going to keep performing the experiment until I get 6 successes. So X is the number of trials required to get 6 successes. For the binomial distribution, X was the number of successes observed in N trials. Here, X is the number of trials required to get some specified R successes. The probability mass function is given here, and we have a special case called the geometric distribution when R equal to 1. So this means that we are looking at the number of trials required to get the first success. We also have something called a hypergeometric distribution. This distribution comes up when we are sampling from a finite population, but we are sampling without replacement. So the example given here is that we have an urn which contains a total of capital N cards. Of these, M are cards of one type, say S cards, and this means that capital N minus capital M cards are of the other type. So let's say N cards. So I draw a sample of size small n. My random variable is the number of S cards in the sample. It can be shown that the PMF is the expression given on the last line of this slide. So we'll skip the inverse hypergeometric and come to the next important distribution, which is the Poisson distribution. Now, the Poisson distribution comes up whenever we are looking at a random variable which can be considered the number of counts of an event. The practical examples of this are when we are looking at events like birth, death, accidents, misprints, and so on. So, if we are trying to model the mortality of a country or the death rate of a country, our underlying distribution for the number of deaths, number of births, etc., should always be the starting point should always be the Poisson distribution. Now, there are more complicated distribution for counts. You will see that the Poisson distribution has a particular property which may or may not hold for all counts. But for the purpose of this class, we will assume that the distribution for count type of variables is a Poisson distribution. So you have some examples here. One could be the number of particles emitted by some radioactive source in a specified time. The road accidents in a year on a given road. The annual visits of a patient to a doctor, the number of rivers in a country. Now you note that whenever we say the number of events, we always have in mind some space or some time period. So it's events occurring over some space or events occurring over a time period or both time and space. So the time and space must be defined for this experiment to be meaningful. The probability mass function then is given by f of x equal to e to the power minus lambda, lambda to the power x by x factorial, and the values of small x are 0, 1, 2, so on, non-negative integers. It can be shown that the property of the Poisson distribution is that both the mean and the variance are equal to the quantity lambda. Lambda is the parameter of the Poisson distribution which occurs in the PMF. So the Poisson distribution has a strong property, which is that the mean and the variance must always be equal. So if you have a distribution of counts and from your sample it seems that the mean and the variance are very different, then probably you don't have a sample from a Poisson distribution. But we're not really going to look at any alternative distributions for count type data for which are complicated and outside the scope of this class. The most common distribution for count data is always the Poisson distribution, regardless of the strong assumption which it makes. Similarly, whenever we look at a continuous outcome, our starting point is usually the normal distribution. So, on the first day, we looked at an overview and we looked at an example of testing whether the weight distribution in a population has changed over time or not. We assume that the weight was normally distributed. So there are four examples of normally distributed variables here. One is height, one is weight, one is IQ, one is measurement error. So the phenomenon which makes the normal distribution appropriate for them is that these are all continuous variables. Continuous variable means that within a certain range, the variable can take any value. For the normal distribution, actually, the range is minus infinity to plus infinity. Now, obviously, you cannot think of a height or weight or IQ which is negative. So this is not really an important restriction. Even though we might be dealing with a random variable which is positive, we still use the normal distribution. The reason comes from the shape of the normal distribution. So on this line, you see the probability density function of the normal distribution. For discrete variables, we have probability mass function. For continuous variables, the corresponding function is the probability density function. The probability mass function, the way to use it is to find the probability of the variable taking some specified value. For example, I said if you want to see the probability that you observe 5 successes in 10 trials, you would substitute the values 5 for small x in the expression for the PMF. Now, for a continuous distribution, actually, we use the probability density function in a slightly different way. We use it to find the probability that the random variable lies in a certain range. So not the probability of taking one specific value, but the probability of it lying within a certain range. You know that the two parameters of the normal distribution are the mean and the variance, and these are typically denoted by mu and sigma square. So we have here the normal probability density function. You can see it's highest at the point mu. In fact, it is symmetric around mu. And you also see that on the x-axis, there are 2 points which are marked. One is mu plus 1.96 sigma and one is mu minus 1.96 sigma. So the way to use the probability density function, if for example, we wanted the probability that a random variable, a normally distributed random variable, would take values above mu plus 1.96 sigma, the way to do it is to mark the point mu plus 1.96 sigma, draw a vertical line from that point up to the curve, and then shape the area for which we want the probability. So here we want the probability of x being larger than mu plus 1.96 sigma, which means we want the area to the right of mu plus 1.96 sigma. So it can be shown that this area is 0.025, which means that the probability of a normal variable being larger than mu plus 1.96 sigma is 0.025. Similarly, say if I wanted the probability of the normal variable lying between, say, minus 2 and 2, I would mark off the points minus 2 and plus 2 on the x-axis. I would draw vertical lines from each of the 2 points up to the point where they meet the curve. So this generates a particular area, and I would calculate the value of that area to get the probability of the random variable lying between the 2 corresponding points on the x-axis. This is how you use a probability density function. So, anyway, the point which brought me to this slide was to say that even if we are modeling a random variable which does not take negative values, it's still okay to use the normal distribution. The reason comes from the shape of the normal distribution. So, this shape is called the bell shape. You can see it looks like a bell. It's highest in the middle and then it drops off in a symmetric way on both points. Now you should also see that it drops off to a very low value. So at one point, the probability to the right or the probability to the left will practically be zero. So this is why if we are modeling, say, weight, and we assume a mean of, say, 50 kilos, so say mu is 50 kilos, the probability of it being below a certain weight will, for all practical purposes, be zero. So even though it won't exactly theoretically be zero, it will almost be equal to zero. So this is why, even though you are using a random variable which essentially takes non-negative values, it's still okay to use the normal distribution. So as I said, the normal distribution is very popular in statistics for certain probabilities, for certain properties which it has. And that's why whenever we model a continuous distribution, we usually almost always start with the normal distribution. If you want the algebraic expression for the probability density function, it's the expression which is given here. So if we have a normal distribution with mean mu and variance sigma square, the probability density function is 1 over sigma times root over square 2 pi times e to the power minus 1 over 2 sigma square times x minus mu whole square. It turns out that the mean of this distribution must be x and the variance must be sigma squared. So normal distribution is very popular for certain properties. One, you can see it's symmetric about mu. It's moderately peaked and it has a thin tail. So the chance of getting outliers from the normal distribution is very small. If you have a data set where you have lots of outliers, then you probably don't have a normally distributed outcome. Now, the normal distribution has this property which becomes important when you perform a test of hypothesis, which is that if we have a normally distributed random variable with parameters mu and sigma, we can construct another random variable. This is obtained by standardizing x. By standardization, I mean that you subtract the mean mu and you divide by sigma. So x minus mu by sigma is a new random variable, and it's possible to show that this also has a normal distribution, except that the parameters are now 0 and 1. So the mean of this new random variable is 0 and the variance is 1. This kind of a random variable is called the standard normal variable. It turns out to be very important when you do testing. So we saw the expression for the PDF of the normal variable on the previous slide. You can substitute mu equal to 0 and sigma equal to 1, and you can get the PDF of the standard normal variable. It will be 1 over root over 2 pi times e to the power tau square by 2. So this notation, if you are not familiar, it says x minus mu by sigma equal to tau. Tau is a new random variable. So this is kind of historic notation which is used for the standard normal variable. So we looked at one class of probability distributions. So each of these, the binomial, the Poisson, the negative binomial, the normal, the hypergeometric, they're all examples of probability distribution. So probability distribution, it means that we refer to the probability mass function for a discrete variable or the probability density function for a continuous variable. And as you saw, we can use them to get the probability of my random variable taking a particular value or a particular range of values. Now, when I make this statement, I'm referring to the population. So, for example, if I'm looking at a height distribution and I want the probability, x is the height, and I want the probability of x being between 5 feet and 5 feet 3 inches, I'm referring to the target population. So, what percentage of people in the target population have a height between these two values? What is the probability that someone in the target population has a height which lies between these two values? For purpose of inference, we are also going to use probability distributions, but these probability distributions are slightly different. If you remember the overview lecture in the first class, we defined what is called a sampling distribution. So in this case, we also calculate probabilities, but we don't calculate these probabilities over the population. We calculate the probability over repetitions of some experiment. So the distribution of any statistic, so if you remember, statistic means a sample value, like the mean, median, they're all examples of statistics. So the idea is that if we take one sample from the population, we can get one value of the median. If we take another sample, we get another value of the median. And similarly, for every sample which I take from the population, we can get a value of the median. So if I look at this collection of medians, I can define some probability distribution over this set of values. This is the idea of a sampling distribution. So note the difference between the probability distribution and the sampling distribution. One refers to some underlying target population, and the other refers to repeated samples from some population. So here is an experiment. So let us suppose we have a population. The population is very small. It only consists of 5 different values. So we indicate them by 5 different colors. We don't know what they are. We don't also want to know what they are. We want to know what the population mean is. So for us, it's enough to know what the population mean is. So what do I mean by population mean? I mean all possible values in the population divided by the number of people in the population, which in this case is 5. Now, suppose I don't really have the time to observe the whole population. I can only draw a sample of size 2. So let me draw two members from this population. Let me denote them by x1 and x2. So if I want to know the mean of the population, my best guess would be the mean of these two values or the sample mean. So this is given by x bar equal to x1 plus x2 divided by 2. So we have 5 numbers. They're denoted by question marks, so 5 different colors. We don't know what they are before we pick them. So let's say I pick the red number and the green number, and they turn out to be 2 and 8. So in that case, my sample mean is 5. Now suppose it's possible to do this sample again. So let's say you do it and you pick the blue and the brown numbers, and they turn out to be 10 and 3. Then your value of x bar is 6.5. So for every value of Every time we repeat the sample, we will get one value of x bar. My value is 5, yours is 6.5. Similarly, somebody else can get 10. If we think over all possible samples, we will get a large set of numbers, and we can think of some probability distribution over this set of numbers. So this is the idea of a sampling distribution. We make a distinction between two kinds of sampling in statistics. One is with replacement sampling and one is without replacement sampling. So I referred to the without replacement sampling briefly in the context of the hypergeometric distribution. So suppose we have some finite population with replacement sampling. So suppose we want to draw a sample of size small n, then after I draw the first unit, however, before I draw the second unit, I replace the first unit in the population. So suppose I draw the first unit and it turns out to be 2. I replace the 2 in the population before I draw the second unit. So the 2 has a chance of occurring again as the second unit. Similarly, I replace the value drawn at the second unit before I draw the third unit. This is called sampling with replacement. I can also think of sampling without replacement. In this case, if I draw 2 at the first instance, I don't replace it when I draw the second unit. So the value 2 has only one chance of occurring in the sample. So you can check that if we have a population of size capital N and we want to draw a sample of size small n, in case of sampling with replacement, the total possible number of samples is capital N to the power small n, because at each draw we can draw any one of the capital N samples. And for sampling without replacement, the total number of samples is capital N choose small n, which is capital N factorial divided by small n factorial into capital N minus small n factorial. However, what is important for us is that regardless of whether we sample with replacement or without replacement, there is conceptually a very large number of samples, and hence conceptually a very large number of possible values of my statistic of interest. So in this case, for the example I was referring to, my statistic of interest is x bar. So these are all possible values of x bar, 5, 6.5, 10, so on. This distribution is called the sampling distribution. Now, just like I don't know the target population, I also don't know the entire sampling distribution of x. The reason is that this set of values, 5, 6.5, 10, so on, it's only something conceptual. In practice, I would only draw one sample and I would only observe any one of these values. So the best I can do is to use the one value which I have drawn and try to make the best possible guess I can about the underlying population. So this can be done by using the information I have on the sampling distribution of my test statistic. So let's try and make that a little bit more concrete. So we looked at some probability distribution. Let's now look at some sampling distribution. So again, let me think that I have this kind of a setup where I'm repeating some experiment. Each experiment can result in one of two outcomes, which is success or failure, the probability of success is constant over the small n repetitions of the experiment. Let me assume that the probability of success is pi. So the probability of the complementary event, failure, must be 1 minus pi. Now let me assume that what I'm interested in looking at is the total number of successes in the sample. So there is some notation on this slide. I am repeating a binary experiment small n times. For the first outcome, I define x1. So x1 I say will be 1 if I have a success and 0 if I have a failure. Similarly for x2, x3 up to xn. Then I can sum all the xi's. It will give me the total number of successes in n repetitions of the experiment, which is the total number of successes in my full sample. I denote this by S. Now, if I could draw multiple samples, which means that if I kept repeating this set of n trials, I would get many values of S. So I can think of probability distribution over this set of values of x, and it turns out that this probability distribution is also binomial. So try and understand that we have defined two binomial distribution, one over the population, and here another binomial distribution, but this one holds over repetitions of the sample. So if we were to keep repeating the experiment, it's possible to show that in repeated experiments, the distribution of S is also binomial and it follows a binomial distribution with parameters n and pi. Now, we have this property of the binomial distribution that if we have many identical and independent binomial distributions, we can add them up and we can still get the binomial distribution. The parameter pi will remain the same, but the first parameter, the size parameter, will get added. So in the last line, I have the result that if x1, x2, xn are each IID means identically and independently distributed, binomial random variables, each having a distribution m pi, it's possible to show that the sum has a binomial distribution also. The size parameter becomes nm and the probability of success remains pi. We can similarly have properties from the sampling distribution of a Poisson variable, which is that suppose we have x1, x2, xn, each of them being a sample from a Poisson distribution with common parameter lambda. The parameter has to be the same. And if we define the sum x1 plus x2 plus xn, which is the total count of whatever event we are observing, the total count in the total sample, it's possible to show that the sampling distribution of the Poisson random sum, it's possible to show that the sampling distribution of S is also Poisson. The parameter now becomes n times lambda. If we are sampling from a normal distribution, then we have some interesting results. So let me assume that I have an underlying normal distribution, so a normal distribution of the population with mean mu and variance sigma square. So let me suppose, for example, that we are looking at heights. x1 is the height of the first person, x2 is the height of the second person, and so on. Xn is the height of the nth person. So these are samples from a normal distribution over the population with some average population height and some average population variance. We assume that we have a random sample So that's the same thing as saying that the n observations are independently drawn. And we define S as the sum of all the x's, the sum of all the heights of all the n heights. And we define the sample mean, which is the mean of the heights of the n people I have observed. Now, there is an interesting result which says that the sample mean also has a sampling distribution which is normal. So, if the population distribution is normal, the sampling distribution of x bar is also normal. The mean parameter remains the same. The variance becomes sigma square divided by the total number of samples. Now, just like we can think of the sampling distribution of the mean, we can also think of the sampling distribution of the variance. So for every one of the samples I draw, I can calculate a variance. And over all possible samples, I will get a sampling distribution of the variance. So if the mean is known, we define the variance in this way, which is we look at the number of squared deviations over the from the known mean and we divide it by n. If the mean is unknown, which is the more common case, then we look at the sum of squared deviations from x bar and we use the divisor 1 over, if we use the divisor n minus 1. So just like we have this result for the sampling distribution of the mean, which is that it is also normally distributed in repeated samples, we can think of the distribution of the sampling variance. So you may or may not have seen this distribution before. The sampling variance has what is called a chi-square distribution. Now we can define the chi-square distribution more generally. If we have xi following a normal distribution with parameters mu and sigma, we standardize the xi's as xi minus mu over sigma, and we look at the sum of squared standardized values. You can see that in the middle of this slide. On the right hand side, it's summation I1 to n, xi minus mu over sigma whole squared. Now, on the left, the notation which you see, which looks a little bit like an X, but not quite, it stands for chi-square. It's a Greek letter, chi. This distribution is said to be a chi-square distribution. We saw that the normal distribution has two parameters, mean and variance. So like that, the chi-square distribution also has a parameter. This parameter is the degrees of freedom. So this is just the definition of a chi-square variable. We construct several, in fact n, standard normal distributions. We square them and we add them, and the quantity which we get, its distribution is defined to be the chi-square distribution. So because x is continuous, the chi-square distribution is also continuous, and the probability mass function, the probability density function, is the expression which is given here. So it's possible to plot this distribution, and you can see that the chi-square is an example of a skewed distribution. So if you have a continuous variable which is non-negative and has a skewed distribution, one candidate probability distribution which you could use is the normal distribution. Similarly, we define what is called a t distribution. T distribution, you may not have heard about the distribution, but you may have heard of t tests. So that is really the reason why the t distribution is important in statistics. So this is how the t distribution is defined. You can define it through the probability density function, which is given on this slide. So if you want to understand this notation, you have f of small t is equal to you have a fraction. On the numerator, this notation stands for the gamma function. So you have the gamma function evaluated at n plus 1 by 2 in the numerator, and on the denominator you have root over n pi times the gamma function evaluated at n over 2, and then all of this multiplied by the term 1 plus t squared by n to the power minus n plus 1 by 2. The range of range of t, like the normal distribution, the range of t is also unrestricted, which is from minus infinity to plus infinity. Now, this is a rather complicated expression for the probability density function. This is not really how we remember the t distribution. You can define the t distribution through its probability density function, but the more common way to define the t distribution is the expression given on the second line of the slide. So this is saying that t is equal to some fraction. So if you have a fraction where the numerator has a definition, which is standard normal, the notation for this is tau, and the denominator has a distribution which is square root over chi square divided by the degrees of freedom of the chi square, then the resulting distribution of this fraction is a t distribution with n degrees of freedom. So why is this important? It's important because it will come up in testing. It's difficult to motivate its importance generally. It's important because of the application of the t distribution in testing. So this distribution is symmetric about 0. However, it is leptocratic, which means that the tails are much heavier than the normal distribution. I said that the chance of getting an outlier from the normal distribution was practically 0, because if you look at the shape of the normal distribution, it is bell-shaped, which means that the curve very rapidly falls off to 0 on both sides of the mean. So this does not hold for the t distribution. If you try to plot this function, you would see that the tails remain quite high for quite a large range of values. So outliers can occur much more commonly for the t distribution. Now, some of you might have heard of an ANOVA test and of something called an ANOVA and the corresponding F test. So the F is also, it can be defined through its probability density function. It's also the distribution of a continuously distributed random variable. The probability density function is the expression given on the last line. You can see it's even more complicated than the expression for the t. Now this notation, if you are not familiar with this, the first term is n1 by n2 divided by, so that is the beta function. Beta function evaluated at n1 by 2 and n2 by 2. Now it's not really necessary for you to know the PDFs of the t and the n by heart. We also don't remember the PDFs of the t and the f by heart. What we remember and how we recognize the F distribution in statistics is by the expression given in the second bullet point. So if you ever come across a fraction where the numerator is a chi square, it's denoted by chi1 square. So it's a chi-square random variable with n1 degrees of freedom, and the denominator is chi2 square, which means another chi-square random variable divided by its degrees of freedom, which is n2, and chi1 square and chi2 square are independent, then the distribution of this resulting fraction will follow what is called an F distribution. If you were to work out its probability density function, then it would be the density function given on the last line, which is the density function of the F distribution. Now we don't, just like I said that height, weight, these follow normal distribution. It's kind of difficult to think of a random variable which will follow an F distribution. So these distributions like the T and the F, they're important because they come up as sampling distributions of certain statistics, and their application is in testing. So we will see concrete examples of this. For now, just note that these are some common sampling distributions. So let's go back to the normal distribution. Suppose I have a random sample from some normal distribution, x1, x2, xn. They might be n weights or n heights taken from some underlying population. We saw that the sampling distribution of x bar is also normal. So if the population distribution of x, of x1, x2, etc., if each of these follows a population distribution which is normal with parameter with mean equal to mu and variance equal to sigma square, we saw that the sampling distribution of x bar, is also normal with the same mean mu and variance sigma square by n. So let me suppose that sigma is known. I can define this standardized quantity, which is tau equal to x bar minus its mean, which is mu, divided by its standard deviation, which in this case is not sigma but sigma by root n. So this is equal to root over n times x bar minus mu divided by sigma. So we know that when you make this kind of a standardization on a normal variable, we get a standard normal variable, which means a normal variable with mean 0 and standard deviation 1. If mu is known, we can also define this chi-square variable, which just follows from the definition. So if xi is normal mu sigma, x minus mu by sigma is normal 0, 1. We can square these and add them up. And by definition, we have what is a chi-square distributed random variable with n degrees of freedom. If mu is unknown, we replace x bar by mu, or we replace mu by x bar, and we end up with a chi-square n minus 1 degrees of freedom. So the degree of freedom is reduced by 1 because we have to estimate mu. If sigma is unknown, note that, so consider this ratio. On the numerator, we have x bar minus mu. So let's write this as root over n times x bar minus mu by sigma. In the denominator, we have s by root n. Let us write this as square root over n minus 1 s square divided by sigma square. And then to get rid of this extra term, n minus 1, I divide by n minus 1. So I have brought in the sigma in the numerator and the denominator, and I brought in the n minus 1. I multiplied and divided by n minus 1. So why did I do something like this? If I do this, then note that in the numerator, I have root n times x bar minus mu by sigma. So from the previous slide, my root n times x bar minus mu over sigma is a standard normal variable. So this means that in the numerator, I have the standard normal variable. On the denominator, I now have n minus 1 s square, square root over this, n minus 1 s square by sigma square divided by n minus 1. So what's the relevance of this? The relevance is that we saw that this quantity n minus 1 s square by sigma square, it follows a chi-square distribution with n degrees of freedom. So look at the last line on this slide, we have a ratio, where on the numerator, we have a normal variable, standard normal variable. On the denominator, we have a chi-square variable divided by its degrees of freedom. So square root over a chi-square variable divided by its degrees of freedom. So what's the relevance of this to us? The relevance is, go back and look at the distribution of the t. The t was defined as the ratio of two random variables. On the numerator, you have a standard normal distribution, and on the denominator, you have a chi-square variable divided by its degrees of freedom. So that's exactly what we have for this normal case. So we have a normal mean and normal variance, and we can use them to construct a ratio where the numerator is standard normal and the denominator is, the numerator is constructed using the mean. The denominator is constructed as a function of the variance. It ends up as a ratio where the numerator is known to have a standard normal distribution. The denominator is known to have a chi-square distribution. It's possible to show that the mean and variance are independent. We're not going into that. But by definition, then we have what is called a t-distribution. Now, the t-distribution has a parameter which is degrees of freedom. This is the same as the degrees of freedom of the chi-square. We saw that the sample variance of the we saw that the sample variance is a chi-square with n minus 1 degrees of freedom. Hence, the t will have a distribution with n minus 1 degrees of freedom. So let's summarize all this. Suppose we have some well-defined target population. We know that this target population is normally distributed. We define the sample mean, and we think of taking many samples from the population. And for each sample, we don't just construct the sample mean, but we also find the variance, and we also calculate the ratio which is given here, which is, for every sample mean, I standardize it, and I use the standardized form as the numerator of a fraction. In the denominator, I have the population standard deviation divided by its degrees of freedom. So just like in repeated sampling, for every sample, I can construct the mean, the variance. I can also construct this fraction. And what this result says that in repeated samples, this fraction will have a distribution which is the t distribution with n minus 1 degrees of freedom. So why is this important? It's important because it forms the basis of the t-test. If you have heard of the t-test, this is the basis for the t-test. We will come back to the t-test in much more detail later. But before that, let me note that inference can broadly be grouped into two groups. So there are two basic problems which we consider in inference. The first problem we call estimation. The second problem we call testing. Now, estimation, it comes when we want to make, in both cases, we want to make some statement about a population parameter. So we defined statistical inference before. All of inference is concerned with making a statement about a population parameter. What is the difference then between estimation and testing? In case of estimation, we don't have any previous idea about this value. We want to make the best possible guess for this value based on the one sample which we have drawn. So you see an example given here. Suppose we want to know what is the average per capita income of some arbitrary country, let's say Egyptians. So a priori, we would have no idea about what this value could be. So if we have no value, then we might be lucky to have one sample from this population. So based on this population, trying to make some statement about the average value of for all Egyptians, this is an example of estimation. Estimation itself can be of two types. We might want to give one single best guess. So this problem is referred to as performing point estimation, or we might want to give not one single guess but a range of guesses. This problem is referred to as the problem of interval estimation. So this is estimation, which is trying to make some statement about a population parameter when we have no previous idea about what that value can be. We might want to do point estimation, which is we might want to make one single guess, or we might want to do interval estimation, which is we might want to guess about a range of possible values. On the other hand, suppose that our population of interest was not Egyptians but Indians. And as before, we are interested in the average per capita income. We can think that maybe from some previous news reports, we have some previous idea about what this value can be. So suppose that we have read some newspaper report and we have seen that this value is mentioned, that the Indian average annual per capita income is 10,000. So we might want to test that whether over time the value has remained at 10,000. So in this case, it's not a problem of making a statement about a population without any prior knowledge at all. In this case, we have a statement which we want to either verify or contradict. So this is the problem of testing of hypothesis. We have a statement about a larger population and we want to either say, based on our sample, we want to make some inference about whether this statement can be assumed to be correct or incorrect. So the next set of slides, which I haven't uploaded as yet on the class page, it starts from this area. It starts from looking at the problem of estimation. So as we said, the problem of estimation comes when we want to make a statement about a population parameter, but we have no prior idea about its value. What we do have is we have a sample, and based on the sample, we want to use some characteristic. So you know that a sample characteristic is referred to broadly as a statistic. So each of these, means, variances, medians, they're all examples of statistics. A parameter, on the other hand, is the same quantity, but it's defined in relation to the population. So the population mean is a parameter, whereas the sample mean is a statistic. So we want to use this statistic as the best guess for the parameter. We say that the statistic is an estimator for the parameter. So for example, if our parameter of interest is the population median and our statistic is the sample median, we say that the sample median is an estimator of the population median. We can think of alternative estimators. We could also use the sample mean as an estimator of the population median. Or we might decide to use the sample mode as the estimator of the population median, or perhaps the smallest value in my sample as an estimator, or perhaps the largest value, or perhaps the average of the first and the last values. So based on my sample, I can think of many possible competing estimators for the parameter. And the problem then is to decide which one of these estimators will be the best choice for best guess for the population parameter. So the example which is given here is that suppose we want to know what proportion, what percentage of the Indian population was infected by COVID. So this proportion for this example is the parameter. My underlying target population is the Indian population. Now we have some typical notation in statistics. We saw that the normal distribution, for example, we typically denote it as normal mu sigma square. Similarly, theta is usually, the symbol you see here is the Greek symbol theta. It's typically used to denote a population parameter. So if we don't have any specific population parameter in mind, we're just talking about parameters, the notation which we typically use is theta. So we want to estimate theta. So based on what do we want to estimate theta? Suppose it's possible to take a random sample, and suppose specifically that it was possible to take a random sample of size 5,000 from the total population, which is the Indian population. So note that this is a problem of a binary outcome. For each of the 5,000 people, we ask them whether or not they were infected by COVID, yes or no. Suppose we do this and 1,200 of them say that yes, they were infected. We can define the sample proportion as 1,200 divided by 5,000, which is 0.24. And the sample proportion P, we assume, is our best guess for the corresponding population parameter, which is the percentage of the Indian population infected by COVID. So P is the same quantity except that it is calculated based on the sample, and hence P is a statistic. And because we are using P as the guess for the corresponding unknown population quantity, we refer to P as an estimator. So here again is some standard notation. We have X as a random variable. Let's suppose its underlying probability function, which can be a mass function or a density function, depending on whether we have a discrete random variable or a continuous random variable. Now, typically, this mass function or density function will depend on some parameter. We denote this parameter by theta. Hence, we say that X is a random variable and its underlying PMF or PDF is written as f theta x. So theta can be a single parameter, like it can be the Poisson parameter lambda, or it can be a set of parameters, a vector of parameters. So maybe we have a normal distribution where neither mu nor sigma square are known. So in that case, theta is the vector mu and sigma square. It is the set of two parameters, mu and sigma square. We have a random sample from this population. So let me assume that it's x1, x2, xn. typical notation for a statistic is t, and we write it as t equal to t of x1, x2, xn. So what that means is that t depends on x1, x2, xn. For example, if t is the sample mean, then you add all the xi's, x1, x2, xn, and you divide the sum by n. So in that case, x bar is a function of x1, x2, xn. Similarly, the sample variance can be calculated depending on x1, x2, xn. So both the mean and the sample variance, they're both examples of statistics. Now, suppose we use this particular statistic t to estimate the unknown theta. We say that the statistic t is an estimator of theta. Now, I gave you examples of several ways, several alternative statistics for estimating a population mean. So let me assume that for estimating a population parameter, so let's suppose the population parameter of interest is the mean. I can choose to estimate it by the sample mean, or I can choose to estimate it maybe by the minimum value observed in the sample, the minimum of x1, x2, xn. So how would I decide in a given situation which statistic to use to estimate a parameter? So some will be good estimators and some will be bad estimators. Now, before I can decide whether a statistic is a good estimator or a bad estimator, I need to define some criterion to decide whether an estimator is good or bad. So the next sets of slides, they do this. They look at some alternative methods for typically finding an estimator of a population parameter. So the first one is least squares. The second is maximum likelihood. It's perhaps it's perhaps the most common way of finding an estimator. You can also do method of moments, chi-square methods, and there are also other methods of finding an estimator. The idea is that we have a population, we have some parameter which we want to estimate. We have a single sample from this population, and we can calculate many statistics to use to estimate the parameter. We have several rival estimators for a given parameter. So what we want to do is first we want to look at several principles for constructing these estimators. And next we want to look at some criterion which will tell us which is the best choice of the estimator for a given parameter. So I think that was a lot of material for one class. I'm going to stop here for today. Do you have any questions? So have all of you been able to get onto the class page and all of you been able to access the material? I have uploaded the videos from the previous two classes and also some of the slides. And some of you said that you did not get the invitation, so I'm a little confused about that because the invitation was sent to everybody and some of you have accepted while some of you haven't. But anyway, I have sent you the invitation twice.